Another great webinar, and we're streaming live from Europe, Germany, and from Argentina. So good evening to Joern and Rodrigo. And we're going to talk about engineered wood screws from production to application. Before we go into the webinar's detail and present this detail, obviously, welcome to all of you, and thanks for joining the Timber Design Society webinar series. And a big thanks go to our sponsors who allow us to run this and other events. And it's actually a great pleasure to have Eurotec joining us as a sponsor, and both Rodrigo and Joern are working for Eurotec. Quick notice to all of you out there. So we received many applications for the development scholarships and also the conference scholarships, which the winners have been announced and will be publicly announced later. So congratulations to all winners who are going to the WCT and the ICTB this year. We have research scholarships coming up. The deadline is not until the 13th of June, but please have a look if you are a postgraduate or graduate student or researcher working in the timber space. This is something which might be for you. More information can be found on our homepage. The other thing, we had our AGM in February, and we have a new committee. We have Lisa Oliver as president and Andrew Hewitt as vice president. And we have Björn, who joined for this year. There's myself and Emma and Felix and Thomas Jungsung Lim, who were part of the committee last year already. And we also have Paul Horn, who joined this year. As usual, if you have any topics of interest in technical notes for the journal, please let us know. You can scan this code here and pop in your topic of interest. And also, if you have any topic you want to share in a webinar, please get in touch as well. Upcoming webinars. On the 17th of April, we have a presentation by Peter Corbett from Becca about innovative timber shell structures. And on the 15th of May, we have Peter Robinson from Papua New Guinea Forest Products. We'll talk about the use of plywood decking in timber bridges. Back to today's presentation. So engineered wood screws. We are really lucky to have Joern and Rodrigo talking to us today about these products, which seem simple, but there's a lot of knowledge and technical expertise behind, because although they see simple, just a simple screw, there's many differences, and there's also quite some high-tech process behind the production from all of those. And Björn and Rodrigo will go into those details and explain us how they're produced, but also how those need to be implemented and applied both in design and especially on site later on. So Joern has joined Eurotec in 2014 and is a very hands-on person. So I've met him several times. He was in New Zealand. And yeah, he knows the theory, but he also knows the praxis quite well. And he has worked on many very famous big projects. I'm going to stop my slides so that Joern can get his slides ready. Joern is also leading the Global Technical Advisory Team at Eurotec, which he has built up. And he then was joined by Rodrigo Mendes, who is also part of this team. And Rodrigo has a crucial role in developing the screw design guide, which is already available, and the upcoming CLT design guide. And he's also developing a range of highly load-bearing and easy to install connectors, and part of them will be also presented today. With that, I pass over to Joern and then later Rodrigo for this webinar. So welcome.
Thank you so much, Daniel. So let's share our presentation with you guys. So first, some details about Eurotec. So Eurotec was founded in 1999. So we had our 25th anniversary last year. We are a medium-sized company having 250 employees at the moment and can store 26,000 pallets, which we ship all around the globe at the moment to roughly 58 countries. And we focus on producing screws and fastening systems. I just fly over shortly over the history of Eurotec. So founded in 1999, we had diverse growing phases till we reached the phase we have today. So we grew from a garage to a little town hall to our first own office building for 3,000 pallets, skip to the next building like 3 years later. So after 11 years, we already had 2 new constructed buildings for 7,500 pallet base. Shortly later, we already had to expand again and again. So in 2013, we already had the first new production building. 2016, we needed a bigger production building. 2018, we extended the warehouse. 2019, another warehouse extension, and just the last recent years, we grew in a quite big manner as we did in the past. So we extended the production, doubled it in size, increased the injection molding facilities, and also got a new machine park in 2023, sorry. And last but not least, what we have this year, we have our new machine park up and running, which you see later, which covers all the processes which we can do with partially and fully threaded screw production, as well as our vision. So our new building will then totally add 80,000 square meters to our current premises, which will include a new warehouse and again, an increased production, which will still be at the same township we are in at the moment. Coming to the interesting topic of today, to our wood construction screws. So we have a quite wide range of different screws, which can be mainly separated into partially and fully threaded screws. And there we got dedicated screws, which we especially produce in Hagen, which starts at 4x40 and ends with 13 by 1,400 fully threaded. And this is our panel twist deck range, partially threaded, our constructs fully threaded range, top duo for roofing and facade applications with a separated double thread, and Eurotec having a dedicated head shape to be used either with metal plates or directly on timber to timber connections. Our facilities are all located in Hagen, which is including stamp bending and stamping, cold forging, injection molding, and partially extrusion. But every screw already starts before our production. So we start with the wire. The wire is the basic raw material. So it starts in a steel mill where the alloy we have defined for our screws to be working best are molten in the furnace. Then we have the raw material, which is drawn into a so-called wire. So it's a pulling process that makes the chunk of metal to a long outdrawn wire. The wire gets descaled. It gets pre-drawn, that you have a certain tension already and diameter on the wire. We have an annealing process. Then we come to the final drawing, which goes up to the final diameter. And then we stain the wire, and coating in this case does not mean any surface coating. It's a special soap that makes the wire suitable to be used in the type of forging machines which we have in production. All wire we're producing in Hagen is only carbon steel. We could produce stainless steel and also stainless hardened, but the majority of the screws required in the global demand is still the carbon steel screw. The next step, the wire comes to our production and is supplied on so-called cones. Those cones are always around 1 ton of weight. And then we have up to 8 follow-up steps that really start with the raw wire and go into the machinery. First stage, the wire is inserted. That means the cone, you uncoil it like you would call a thread for when you're sewing. You put it in the machine, and then it comes into a so-called feed roller. The feed roller makes the wire straight in horizontal and vertical alignment, and then a pre-straightened wire comes directly in the machine. That means we already move first irregularities by these feed rollers, that the wire really is like a straight piece of metal. The next step is the wire is cut into pieces. Most people think for an 8mm screw, for example, you need an 8mm wire. In this case, it's wrong. We have a 5.71mm wire because the wire gets rolled out in the thread rolling process. So always the wire diameter can be seen if you measure between the thread or on the shank. This gives you an idea of the wire that has been used, and also the wire we use in the first step, or in this case 3.2, is shorter than the end screw project because the wire gets also stretched and rolled out in length. First step for us after drawing the wire is the forging. We forge the heads in 2 different steps. The first step is just volume, which looks a bit like a mushroom. And the second step is then in this case geometry, where the type and the length as well as the torque drive gets forged in. So the pre-forging is the volume, the final forging is geometry, and also there the milling ribs and the full geometry and all sharp details of the heads are forged in this first bulgy piece of metal, which is created by pre-forging. Then comes the thread rolling. Now we talk mainly about partially threaded screws. So the screws get turned, you will see a video later, and then we roll on the thread as well as also the milling ribs behind the shank. This is done by matrices, which have a dedicated pressure where the wire gets pulled in between and then it rolls over the wire and creates the full thread geometry and also lengthens the screw in a certain way, as well as you see on this lower piece, which you see completely on top of the picture and complete in the bottom. Those are the matrices that are rolling the spiral curl behind the thread. We have different types of tips. So people might know the type 17 cutting notch, which is also then milled out. So if we have the cutting notch in the screw, this is a separate step, it's milled out. Other tips like drilling tips, they are pinched by a pinching process, and our proprietary IG tip, which just allows a faster biting of the screws, is rolled with the thread. So there is no dedicated process creating our AG tip. So this is done even still on the same machine. In the end, a robot grabs the screws and puts them in a sorted manner in the boxes. And they need to be sorted because otherwise they would tangle up in the next processes, like in the box just by transportation, in heat treatment, as well as in surface treatment. So the screws stay in this sorted manner till they get packed in the box. This is quite important to make the handling overall just possible. So all fully threaded screws start as partially threaded screws, with one exception, which we see later. So fully threaded screws from 600 by 1400 are produced in our CNC roll. That means they are on the left side, get moved in between the wheels you see in the right picture. The CNC catch the initial thread, which we have done on the partially threaded machine, and then they get rolled through the machine, and the belt conveyor drops them again in a sorted manner in a box at the end of the machine. We also have the option for fully threaded screws up to a length of 600. Remember, we just said 600 to 1400 are CNC machines. We also have our Big Bertha, how we call her. She can make up to 10 by 600 in one fully rolled thread in this big process, which is a quite loud and a quite force intense process. But most screws, let's say the screws from up to 400 are done on a separate machine, 4 to 600, one step on this machine, and 600 up to 1400 are done in two steps, first partially threaded, then fully threaded on the CNC. For screws which are short, we say a screw below 200 millimeters, in thicknesses from 6 to 12 millimeters, they can be done on a new multi-stage press. This is a 3 production step machine, which works slightly different than the inline machines that you saw before that. We just had our new arrival last week. It went in production. We received a new machine which can do fully threaded screws. This is a monster of a machine. The weight is 35 tons. We have a forging force of 80 tons. This thing produces 90 screws per minute up to 400 millimeter. We can do 5 kilometers wire per hour with this machine, and we can produce up to 1 meter without leaving the machine on this machine. So it's a quite unique machine, and this increases our demand, which increased massively, of screws of 240 up to 400 with diameters of up to 10 millimeter, really in a big way. The other machines, they are a bit faster. They can do 140 screws a minute, but only partially threaded. Here we can do 90 fully threaded per minute. A little impact on the machine. So here's how it looks. The wire gets straightened and drawn in. We forge the head. Get the full geometry of the head, and the thread roll for the first thread. screws get turned by a robot. They get pinched, the milling point tip on, second thread is rolled on. And then the screws get driven to the end and get picked up by a robot. Put it into boxes, always 10 screws depending on the diameter. In addition, we have our cold forging machine, which can do screws from 4x14 up to 6x120. Those machines work on a revolver principle. They can do 700 screws a minute, but only on 4x40s. The number decreases the bigger the screw gets, but this screw rarely comes below 400 a minute. So this screw is just for the mass production of smaller screws, while it's in the structural screws, 6, 8, 10, 12, 11.3, 13, they get produced in the other machines, which have a lower output, but a much more controlled forging process. In addition, we can create dedicated tips like type 17 tips or the drilling point tip of the machines in case this is required on exceedingly long screw lengths that we might take to switch to those machines. After the screws are finished in Hagen, they get to heat treatment. So we do case hardening, and for the case hardening, all the screws are hung up separately in a rack. The reason is we have an even heat distribution. This again is also a reason why we try to not tangle up the screws, to keep them as separate as possible, that they can be hung in by hand, as you see in the top right picture, in the rack to get into the hardening furnace. In the hardening furnace, we first start with a washing process. That means all lubricants which are left over from production are removed because they will burn into the screw during the hardening process. So this is a quite highly specified project where we have a defined pressure, a defined solution that cleans the screws, and then we go in the hardening furnace. As we talk about case hardening, we first have initial carburizing phase where the screws get brought at a certain temperature for a certain amount of time. This carburizing process separates, for example, fully threaded screws, which have a different process from partially threaded screws, which gives the fully threaded screws a higher hardness than the partially threaded ones and more durability. And then the final heat treatment phase is up to 800 degrees Celsius. After the heat treatment phase, the screws get quenched in an oil. So the oil doesn't cool the screws down too rapidly. It cools the screws down in a bit slower manner. That means the screws are not getting crystallized. The molecular level still stays with a certain ductility and doesn't make the screws too hard. After quenching, the screws get tempered again at 200 degrees Celsius. That means, again, this is done to give the screws the perfect mixture between stiffness and ductility, and to get the molecular grit really to a organized grit, that the screws have the stability we require for the correct use and also the correct values in the structural elements you guys are designing. The heat treatment process, just please apologize, I only had a German picture for that one. So we bring in carbon containing gas in the chamber. This is the carburizing. That means we have carbon that reaches the surface and diffuses towards the core of the stream. Then it's the initial hardening phase. So the hardening is then also at this 800 degrees, which increases the surface hardness as well as giving certain ductilities for the core. Then comes the tempering to reduce the stress in the extremely hard surface layer and gives also the outer part of the screw different ductility. But this is adapted to the requirements we have to our screws. So we have defined in our EDA certain torques we need to reach for breaking of the screw, as well as also a certain bending angle. The bending angle is not defined by the EDA, but we always have a bending angle of 45 degrees at least to assure that we have the correct ductility, but it should not exceed 50 degrees because then they are too soft. So it's always quite a sweet spot we are looking for to have the perfect mixture between ductility and stiffness. For fully threaded screws, the bending angle is lower, for example, than it is on partially threaded. There we always, especially in 8 millimeter, we aim for the 45 degrees. We have our own little chamber furnace, which isn't in operation at the moment, because as you might all have heard, the gas prices in Europe were exploding. So we didn't put it into operation, but this will only be used for screws up to a length of 5 by 100, because there we have a conveyor belt process, and there we don't reach the perfect heat distribution that we aim for on the screws on longer length as well as higher diameters. After having produced and correctly hardened screw, the screw goes on to surface treatment. And in the surface treatment, we do mostly electroplating. In addition, we also have dedicated zinc nickel coatings, our 1000 coating to reach C4 or even C5 values in the C rating. But the majority of the screws, as the just demand is the highest, is zinc plated screws. So the electroplating is done in so-called drums. In those drums are satellites, which are like rectangular blocks that also prevent the screws again from tangling up. So this is also important to keep the detangling during the galvanics process, just to have even distribution of the surface coating, which is at least 5 microns. After that, before they come into the galvanics process, they get washed. Again, all the residues and also, let's say, burned in material from the hardening has to be removed. This is done by degreasing, by pickling, and by electrolytic degreasing to make sure the screws are as pure as possible on the surface. Next step is the electroplating. So it can be a zinc, it can be a zinc nickel alloy, it can be a aluminum matrix flake alloy. So there are different alloys we can apply to the screw. We also apply a passivation, which is another surface protection against the zinc corrosion. And then we seal the screws or even apply anti-friction coatings, for example, on fully threaded screws, just to have an easier assembly torque and let's say, less work for man and machine when they're setting the screws. After the tempering and drying, again, we have another heat treatment process that also is really important for the hydrogen embrittlement, because the surface treatment is the point where you have the highest risk of hydrogen embrittlement to be induced in production. So this is why a really controlled process with controlled temperature and an additional heat and centrifugal process are required to really temper and dry the screw, to keep the ductilities and don't have any hydrogen embrittlement in the screws. Last but not least, the screws come back to Hagen and we go into the packing and commissioning, which is pre-sorting by a robot and then packed by hand based on weight. Our packing requirement says we have a dedicated weight per dimension of the screw. If we are even 2 grams too low, we just add another screw. So especially in small screws, the chance is bigger to have 1 more screw in the box than 1 too less, as we always look for a weight that needs to be as a net weight in the box, that we just know we have the correct amount of screws, because counting would be impossible. And we found no robot that did such a good QC by even looking screws before they get packed in than the human eye and the human workforce can do. Last but not least, for my part, we have a little look at our overproduction, just wrapping up the 10 steps I showed you, which are required to get, as we hopefully always have, the perfect screw. So as you see in the last step, so we have a quite tight quality control process. We control the screws during the production process, the first 10 screws of a batch, every 10 minutes 10 screws, and the last 10 screws when the box is filled up. So the quality control is quite tight, and we are really proud of this quality management. It's all certified by ISO 9001, which means we undergo constant improvement, and also all of our connectors are EDA certified. Just one little remark, as you saw the steaming heads in the video, this is all cold forging. That means we don't bring in any active heat in the process, like with induction or heated up matrices. So just the heat is all produced by the material flow of the machine as mechanical energy is dissipating into heat. So this was all a cold forging process, despite seeing the steam on top of the screws. Yeah, my last slide before I hand over to Rodrigo is just on the certification. So we have our EDA on all of our relevant connectors. We are also now at the moment doing some extended seismic testing, which will be done in New Zealand. More details will be coming quite soon, hopefully. And we also have an ICC for our wood construction screws to be suitable for the American market. But that's it from my side. I will hand over now to Rodrigo, as he will now take over the part of the correct application and use of the screws.
Thank you very much, Joern. So let me see if I can change. So I'll start talking a little bit about our material and coating types for our screws. Our panel twist stack screw, for example, our partially threaded screw, comes in 5 different material and coating types. The most used one is the harder carbon steel with electrogalvanizing, as Joern explained, and also chromium passivation. And they are classified in this chart regarding the use on service class 3, their mechanical resistance, their suitability to use with acidic woods, and suitability to use near the coastal zones. So for the harder carbon steel version, as you can see, it is suitable for use in service class 1 and 2, and it has very high mechanical resistance, but well, it cannot be used on acidic woods and coastal zones. Then we have the exact same screw, but with a special coating. We call it a Dawson coating because it can withstand at least 1,000 hours of salt spray testing according to ISO standards. Although it can't be used on service class 3 according to Eurocode 5, we recommend it to be. This is the one recommended to be used with treated wood. Then we started with the stainless steel versions of our screws. We have the hardest stainless steel C1 version, which is also known as martensitic stainless steel. This one can be used in service class 3. It is just imagine a green tick there. I forgot to put it. And the important thing is that this one can be used on service class 3, and it has by certification, by our ETA certification, the exact same mechanical resistance as the harder carbon steel electrogalvanized ones. Then we also have the stainless steel A2 and A4, which can of course be used in service class 3. And well, the difference between the two of them is that the stainless steel A2 can be used conditionally on very acidic woods, because in long term it can the appearance of it can be a bit damaged. It cannot be used in coastal zones. And the stainless steel A4 version is the strongest one regarding corrosion. So it can be used on oak, for example, and also very near the coastal zones. As you can see, they have a high mechanical resistance. but they are much more ductile as the harder carbon steel screws. So that has to be taken into consideration in the structural design. Then, for you to know the basic mechanical properties of the screws, which are determined with experimental testing, are these: the withdrawal parameter, which is mostly dependent on the pitch of the thread of the screw. So important to determine the pull-out resistance of a screw. Then the head pull-through parameter, which is mostly dependent on the head geometry of the screw. Then also the tensile strength of the screw, which is mostly dependent on the material properties. These three first ones are the ones that are taken into consideration when calculating a connection regarding a screw subjected to axial loads. Then the yield moment, which is determined in a 3-point bending test. No, 4-point bending test, actually, according to the Eurocode standards. And it's the most important mechanical property for lateral loading. Then I'm going to talk a little bit about the features of a wood screw. So starting with the head shapes, our screws come mainly in 4 types of head shapes. The first one is the most used one also is the countersunk head, which needs to be installed flush with the screw surface, and it has a milling ribs which reduce the cracking when installing, which I will explain later. Then we also have the washer head version, which increases the head pull-through resistance of the screw, and it has to be installed above the surface of the screw of the wood. Then the cylinder head, which is present on our fully threaded screw constructs, which is the only head type allowed to be installed further from the flush of the wood. So you can completely conceal it, for example, and then put a plug to hide it. And then our external TX head, which is the head for our largest constructs, fully threaded screw, the 13mm diameter one, which has a maximum length of 1 meter and 40 centimeters. And this one needs an extra torque to be installed. So this head is the most recommended one for high torque transmission. Continuing, then all our screws, except for the external Torx head, has a Torx drive, which has proven to be the best drive for wood screws, modern wood screws, because they allowed a tight grip with the installing tool, reducing the risk of stripping the screw's head, and it allows the highest torque transmission for installation. Then, as I mentioned, the countersunk head, for example, has these milling ribs, which make it easier to put the screw flush with the wood surface without cracking it. Then our partially threaded screws also have this shank cutter, or also called a milling shank, because this part has a slightly bigger diameter than the smooth shank of the screw, and it allows for easier inserting of the screws, because it reduces the torque necessary to install the rest of the smooth shank of the screw. Then we have 3 types of thread for the screws. I'll talk a little bit about them now. Starting with actually, when do you use a partially threaded screw and when do you use a fully threaded screw? So partially threaded screws have the ability to close the gap between wood components because one part is threaded, the other is smooth. So this is also known as an assembly screw, and you use it mostly when assembling CLT walls to CLT walls, and whenever you need high lateral resistance. And fully threaded screws are used to transmit very high axial forces in timber construction. They are mostly used in an inclined direction with respect to shear planes. So they are activated axially and not laterally, and are the preferred screws for reinforcement also. So as I explained, the partially threaded screw, for example, our panel twist tech screws, they are used like this, for example, in a spline connection within a CLT wall or a CLT slab. Where lateral load is dominant. Then also the fully threaded screw is used as a secondary to main beam connections. It can be used depending on the case to even replace a beam hanger, for example, on this application. And it has also the application for reinforcement, as I mentioned. For example, the notch reinforcement, as you can see on the middle image, and this zone of the notch, there are very high perpendicular terrain tensile stresses. So this screw sews this crack when it starts to happen and prevents it to open long term. And also on supports where, according to the actual analytic methods to calculate this reinforcement, they completely absorb the compression perpendicular to grain, also preventing long-term deformations. And the double threaded screw is our top duo. This screw has the ability to transmit the forces between wood components directly, so without compressing the insulation in between, because that's why it's used for facades and as a roofing screw also. Then for the screw, the tip types, we have mainly three types of tips. The type 17 cutting notch, which is the one that has a faster grip on when you are installing. So when you start installing a screw, it will have a fast bite into the wood. So it's has a very fast installation time. Then our proprietary AG tip, which has a more reduced splitting effect and also a reduced screwing torque compared to the type 17. And our proprietary also drilling tip, which is our RBS tip, is the denomination under our certification, which allows further reduce in screwing in torque, and also allows for a reduced requirement of spacing and distances when you are calculating the connection, because you are installing the screw and at the same time pre-drilling it. Then talking a little bit about now the service classes according to Eurocode and corrosion protection classes. So for the service classes, according to Eurocode 5, we have three service classes. The service class, they are related to the relative humidity of the atmosphere and the correspondent moisture content of the wood. So for practical uses, just for you to know, The service class 1 is taken as indoor, completely indoor. The service class 2 is given as semi-indoors or semi-covered. And service class 3 is completely exposed to the elements. Another information is that deterioration agents on the wood start happening when the moisture content of wood is higher than 20%. So this is the key parameter for service class 3. When wood is completely outdoors, it can surpass this moisture content, and then of course the Chilophagous insects or other types of molds that can corrode, that can reduce the cross section of the wood can happen. I mean, then we also have the C categories, the corrosivity categories according to EN 14592, which come from the steel construction. And they depend on many parameters, but to make it simple, they depend on the frequency of condensation that can happen in the atmosphere where the timber connection you're considering is happening, and also another factor is the distance from the coastline. So also chlorine and sulfur dioxide. So this measures the pollution level of the atmosphere. This has to be taken into account when choosing the material and coating type of the screw. We have a very comprehensive chart of this relating our materials to these categories that I invite you to also enter on the website to read it fully. And also the T classes, which are related to the type of wood you're considering, type of wood you are considering your connection. So we have 5 different T classes according to the same EN 14592. And they mostly depend on the moisture content of the wood and the acidic content. The acidic woods like oak, for example, chestnut or Douglas fir, this acidic content can corrode the wood over time. This mostly happens when the wood is wet. When I mean wet, it's between 16 and 20% of moisture content. So it really depends on the wood type you're considering to choose the correct material of the screw. For example, as I mentioned, the stainless steel A4 version of our screws is the only one suited to be used on very acidic woods. Just an exception, not all hardwoods are, not only hardwoods are acidic. As you can see, Douglas fir is one of the most acidic wood types, and it's a softwood. So a little bit of frequently asked questions about wood screws. Is pre-drilling necessary for our screws? In general, they're not required. Okay, just if you want to have a very aesthetic look, okay, so not a single crack and really flush with the wood surface, then you would pre-drill, but mostly it is not required. And then for softwood, right? But for hardwood, it is generally required. We have two types of screws that are certified for screwing without pre-drilling in hardwood. It's our angle bracket screw hardwood, the name of it, which has a very high torque resistance required to be that is required to be installed in these conditions, and also our LBS screw, which comes in a partially threaded version and fully threaded version. And last but not least is a very common question: can I use impact driver when installing wood screws? So we have made some experimental tests regarding this. We have taken many types of our screws with many diameters, partially threaded and fully threaded, and installed them with both methods. So using an electric drill and an impact driver. Then we unscrew them and tested regarding the tensile strength, and also tested the pull-out strength of the drilled ones. And we found out that less than 1% difference was found on performance, concluding that the method really doesn't influence the pull-out or tensile capacity of the screw. Many people ask this because the impact wrenches, they have this very fast impact that that eases the installation of the screws. And there was a debate that this repeated impact on the screw would cause a fatigue failure, or reduce or damage the wood fibers. But we can show you that that it isn't this way, and you can use it without any problems to install mostly long screws with big diameter, which take a lot of torque to be installed. But you always have to remember that they are not permitted to be used on steel to timber connections, because the very high torque when you're finishing the installation onto the steel can damage the head of the screw. And I also invite you on our website to open our brochure on this subject, which shows you the comparison between the electric driver and an impact driver. And you can also check the charts where you see that it starts with a little bit of torque resistance, and the longer the screw, the higher the torque it takes to be installed. And of course, the highest torque of the chart corresponds to the installation of the head of the screw. So this is all for my part. Thank you a lot for your interest.
Well, thank you so much, Joern and Rodrigo. That was extremely interesting, and to see that the wire becoming a screw was really impressive, also for us who specify those screws almost on a daily basis. So great to see the manufacturing process, and Joern and Rodrigo, really nice part in terms of all the considerations on design, from the structural parameters all the way to service classes and corrosion classes. Interestingly, New Zealand doesn't talk about service classes the same way we do in Europe. However, the glue-lump standard does refer to service classes, and I think it would make sense to introduce or start talking about service classes when we design timber structures as well. So we don't have too many questions as yet, so hopefully there's some more coming in. You alluded to ductility and testing happening in New Zealand. Can you give us a little bit more about the use of your screws in ductile applications, like in shear walls with CLT or similar? Or Rodrigo, or one of you?
Well, in Europe, it is required for example, when you have a screw subjected to seismic loading, you are required the screw is required to have a certain ductility, because as we know, for seismic design, we design according to capacity design. We installed, we need dissipative connections, and the connections are given by screws mostly, and the screws need to withstand repeated deformation in a plastic way while maintaining the certain stiffness. And this is given by an experimental testing according to this standard EN 14592, which classifies the screw in low cycle ductility classes. These are 3 types of ductility classes. The 3 is the most stringent one, most strict one, and in Europe, it is required the screw to demonstrate this performance to be used on these conditions. And we have this. We have a brochure that explains this experimental test that we carried out with our screws. So yeah, I invite the attendee to check.
And as I already teased, so we're currently in preparing tests with Thomas Lim in Canberra University to have extensive cyclic testing on our screws according to more New Zealand appropriate methods, which also compares the ductility between high carbon, stainless, hardened martensitic, and also austenitic screws like A2 and A4.
Perfect. That's really good to hear that you're also doing some local testing, which also partially answers one of the next questions. The question, however, was still the tables about the impact driver testing. Is that available in English as well? Because I think the slide was showing German titles.
Yeah.
Yes.
So if you just go on the website and go on support, there you can download all catalogs, and I recommend just to do the impact brochure as well as our screw design guide, because this is where the tables Rodrigo mentioned that show you which screw type and coating allocate to which service class or corrosivity class.
Yeah, thank you. That's very helpful. I quite like the comparison you were showing before. One other question came in. Do you consider acetylated radiata pine as highly corrosive? I think the commercial name is also known as Accoya.
Yeah.
Would
so
you know?
let's say Accoya is mainly used as a decking board or cladding board, and Accoya themselves recommend to have at least stainless steel A2, so an austenitic steel. And we consider it as corrosive class because the acetylated treatment really makes the timber sour and it smells like vinegar even when you're cutting or milling it. And even if you could take, for example, a stainless C1 martensitic screw, but it will cause a black stain as there will be a corrosion happening at least on the surface, making these nice blooms where you need to take oxalic acid to get it white again. So definitely we recommend A2 or higher grade for this type of timber, and also for kebony, which is I think a furfuryl treatment and not acetylatic.
Perfect, thank you. I have one question from my end. We have had a lot of timber construction which was erected and it got wet during the erection phase, and obviously there was the question what happens to the screws. Do you have any general rules of thumb, what you should and shouldn't do, or what a designer should be careful on site when they inspect the site, and at the same side, what should a carpenter, a builder do when he's installing those screws and knows that rain is looming? Do you have any general recommendation you could share with the New Zealand and the wider audience?
So interestingly, I just was on Monday on the big construction site in Netherlands, where they created a 2,000 square meter CLT building, 3 stories, and just going on to the next 33,000 square meter CLT building. And they had a quite distinct moisture control. So they already seal the CLT panels with a foil before they go to site, and on site they immediately seal the joints after they set the fully threaded screws. So first of all, the screws, they sustain a certain amount of, let's say, moisture, direct water, or humidity. But as soon as screws are submerged in water, when they are only zinc coated, this is when the corrosion starts. The good thing is on zinc plated screws, the zinc coating is a bit more mechanically stable than, for example, like a zinc nickel coating, because it's a bit more tight on the surface if the screw is washed correctly. So what we recommend, some people just shove all their screws in buckets and then just carry the buckets from A to B. If the bucket has a hole that water can drain, this is a nice method. So this might work, but also preferred. But if you just put them in a bucket and have them there in the rain where the bucket is filling up, you definitely damage your screws. And also you should, so our cardboard boxes, in the past, they were coated with a gloss. They were quite water repellent, I must say. Just for now, for ecological reason, we removed this just to have plain cardboard. So they will stand a certain time, but the full exposure of your working materials, you should take only the materials you need to the side you're working on and keep the rest stored safely and mostly dry if it's not stainless. Also, we have now the option to get all our screws in big boxes. These boxes stand upright and have a double floor, so when they stand in water, it will not soak up. So moisture is not your worst enemy, but submerging your screws is the thing you should prevent. Inspectors should look at a corroded head, because when the head is already corroded, also there's a big risk the screw has corrosion on the shank. So when you see corroded heads and even standing water maybe in the torques, you should try to remove the screw if you still can, if there's no fracture already within the shank. So white rust, red rust is your enemy.
Sorry, what is white rust?
The white rust is when the initial corrosion sets. This is like a protective patina, but the red rust is when you already have material loss in the steel.
Interesting. Learn something new. Perfect. So there's no more technical questions. There's one who asked about if the presentation will be available. And yes, a recording will be uploaded in due course. Rodrigo and Joern, thanks again for
One more question is coming, I think. Just one more jump in.
Yeah. So the New Zealand code specifies a 5 diameter edge distance. Can we have smaller dimensions 3D, or what influence does the edge distance limit, in your opinion?
I wouldn't know it to Rodrigo because he just already teased this with reduced spacings on the drilling tip.
I don't have by faith the requirements, but can we use smaller dimensions, e.g. 3? I will really have to check the charts, but maybe our drill tip screw can do it.
So we don't know the NZ code, but according to ETA and Eurocode, our drill point tip, which we have on construct 6.5, 8, and 10, they can reduce the spacings to up to 3D in between the screws as well as to the edge.
Perfect. Right. Again, I think that is all from a technical end. Thank you both for sharing your knowledge and expertise. It's, again, very impressive. And thank you also for making yourself available so late at night for us in New Zealand. So thanks again. And I'm also looking forward to see Rodrigo at the International Conference of Timber Bridges, where you will present, I understand. And yeah, obviously, Joern, hopefully you're back soon in New Zealand as well. And
definitely,
you can then catch up with all the engineers out there who are specifying timber and timber screws. Perfect.
I will first be on the Brisbane WCTE and then come over to Rotorua. So we'll be there both in June.
I see you both then. Perfect. Thank you so again. Thank you so much again. And thanks everyone for joining in. And I see you all at the next webinar in April again. Thank you and goodbye.